Proxima Centauri is 4.2 light-years away. At our fastest spacecraft, you arrive in roughly 70,000 years, dead. Your grandchildren's grandchildren's grandchildren, also dead. Everyone assumes the speed of light is simply a speed limit. It is not. It is a wall baked into the geometry of space-time itself. But physicists have been working the problem. We are going to walk through every serious proposal. Alcubierre's warp bubble, the exotic matter requirement that seemed to kill it, the Casimir effect, the EmDrive, and why it collapsed under scrutiny, and the Lentz breakthrough that changed the math. We will look at wormholes and what threading one would actually require. If you want to follow this series, subscribe now. The journey starts here. There is a star you can see with the naked eye on a clear night in the southern sky. It sits so close to us, astronomically speaking, that astronomers gave it a name that means nearest, Proxima Centauri, 4.24 light-years away. On any map of the galaxy, it is practically in our backyard, and yet that distance, when you begin to feel it in your bones, stops being a number and becomes something else entirely. It becomes a wall. Think about what 4.24 light-years actually means. Light itself, the fastest thing the universe permits, takes 4 years and nearly 3 months to cross that gap. We send a beam of light from a telescope on Earth tonight, and it will not arrive at Proxima until the middle of the next decade. 4 years. For light. For us, the species that took 70,000 years to walk out of Africa and spread across a single planet, that number demands a reckoning. Here is a way to feel it. In 1977, we launched Voyager 1. It is the farthest object humanity has ever placed in space. Right now, as you read this, it is screaming away from our star at roughly 38,000 miles per hour. That is fast. It is faster than any bullet ever fired, faster than any aircraft ever flown, faster than anything our civilization managed to build for most of its existence. 38,000 miles per hour feels like it should be enough. It is not even close. At Voyager 1's speed, the journey to Proxima Centauri would take approximately 73,000 years. Your entire civilization, every monument, every city, every language, every record of every human being who ever lived would be ancient dust before the probe passed through that star's outer atmosphere. 73,000 years to reach our nearest neighbor. A neighbor so close it has its own exoplanet, one sitting inside the habitable zone, one that might have liquid water on its surface right now. A world possibly capable of holding life, and we cannot reach it in any span of time that our minds can hold without flinching. We tend to talk about interstellar travel in the abstract, the way we talk about retirement or the long-term future of the species. Someday, when technology advances, when we are ready. But the gap between where we are and where we would need to be is not a gap that gradual engineering progress can close. We are not talking about building a faster rocket. We are talking about crossing a chasm that makes every speed record in human history look like a child's first steps. The mission you are imagining, the one we are going to plan together across the rest of this story, is a voyage to Proxima Centauri. A real voyage, one that arrives within a human lifetime, one that does not require thousands of generations of descendants born and dying inside a metal cylinder drifting through the dark. That is the mission. And right now, with the tools we have, it is impossible. The question we need to answer is whether it has to stay that way. To answer that, we have to understand why Voyager 1, already the fastest traveler our species has produced, barely moves the needle. Because if the fastest thing we ever built is still 73,000 years short, maybe the problem is not the engine at all. Maybe the problem is speed itself. In the summer of 2018, a spacecraft the size of a small car flew closer to our star than any human-made object in history. It broke every speed record we had set in 4,000 years of recorded engineering. And it did so in a way that made the laws of physics feel almost generous. The Parker Solar Probe reached 430,000 miles per hour, more than 11 times faster than Voyager 1. For a brief stretch of its orbit, it became the fastest object humanity has ever created. You might feel something shift in your chest when you hear that number, 430,000 miles per hour. That is fast enough to fly from Earth to the Moon in less than 40 minutes. Fast enough to circle our entire planet in under 4 minutes. When you sit with that speed, really picture it, the number feels like a breakthrough, like the kind of achievement that changes what is possible. We are about to calculate what that number actually means for the mission to Proxima Centauri. Prepare yourself. At 430,000 miles per hour, the journey to Proxima Centauri would take approximately 6,500 years. That means if we had launched the Parker Solar Probe toward Proxima, the year the ancient Egyptians were building the pyramids, it would be arriving roughly right now. The entire arc of recorded Western civilization, every war and empire, and invention and revolution, would barely cover the duration of the transit. And remember, this is the fastest object humanity has ever produced. Our absolute record. The peak of everything our species has achieved in propulsion engineering across its entire existence. What the Parker Solar Probe reveals is a problem with our entire framework for thinking about interstellar travel. When we go from Voyager's 38,000 miles per hour to Parker's 430,000, we multiply our speed by more than 11 times. The journey time drops from 73,000 years to 6,500, a massive relative improvement that leaves us completely stranded. We are still talking about thousands of years. The math does not care how impressed we are. This is what physicists mean when they say the challenge of interstellar travel is not engineering but physics. You can build a faster rocket. You can solve the fuel problem. Engineers can design a sleeker, more efficient spacecraft, and you will still arrive at Proxima Centauri in a time frame that makes the mission meaningless for any individual human, any generation, possibly any civilization with a recognizable continuity. Speed, raw kinetic speed through space, is the wrong tool for this job. The mission we need requires something that does not behave like a rocket at all. The Parker Solar Probe is the peak of one mountain, and from its summit, you can finally see the shape of the problem clearly. You are looking at a completely different kind of terrain. But before we can find a way through, we have to understand why going faster through space has a hard ceiling. A ceiling that every physicist in the world agrees on. A ceiling that comes with a warning written in the mathematics of the universe itself. And that ceiling has a name. Most people have heard it. Very few people have really sat with what it means. In 1905, a 26-year-old patent clerk in Bern, Switzerland, sat down and wrote a paper that changed the structure of reality. Albert Einstein was not working at a university. He had no laboratory, no team, no institutional funding. He was processing patent applications by day and thinking about light in his spare hours. What he produced in that paper was the special theory of relativity, and buried inside its elegant equations was a sentence the universe has been enforcing ever since. Nothing with mass can reach the speed of light. This is not a practical limitation, the way a car cannot go faster because the engine overheats. It is a mathematical impossibility baked into the deepest layer of how the universe operates. To understand why, you have to understand what Einstein actually said about energy and mass and motion. When you accelerate an object, you add energy to it. The faster it goes, the more energy you have put into it. This is ordinary, intuitive physics. But Einstein showed that as an object with mass approaches the speed of light, something strange happens to the relationship between energy and speed. Each additional unit of speed requires more energy than the last. The closer you get to light speed, the more energy each additional tiny increment of speed demands. The curve does not flatten out, it steepens. It steepens without limit. At half the speed of light, you need a lot of energy to accelerate further. At 90% of light speed, you need vastly more. At 99%, the amount of energy required is staggering. At 99.9%, the calculation produces a number that would strip the words from your mouth. and at 100% the speed of light itself, the math demands infinite energy. The equation does not produce a very large number. It produces infinity. And infinity is not a destination you can fund. This is the wall. Every spacecraft, no matter how brilliantly engineered, no matter how perfectly fueled, runs into this wall if it carries mass. You and your crew are made of mass. The ship around you is made of mass. Every kilogram aboard requires infinite energy to reach light speed. The universe is not saying it would be very expensive. It is saying the cost is literally uncountable. No amount of fuel, no reactor, no exotic power source can supply what the equation demands, because the equation demands everything. For almost a century after Einstein wrote that paper, the standard interpretation was simple. Faster than light travel is impossible. The end. There are stars in the night sky that the laws of physics will simply never allow us to reach within a human lifetime. We can look at them. We can send radio waves that will arrive in our great-grandchildren's era, but we cannot go there. The wall has no door, and for a while, that conclusion sat inside physics like a fact of nature, something to accept, a boundary drawn by the universe and enforced by mathematics. Except there is a second theory of relativity. Einstein wrote it 10 years later, and it contains a clue that changes everything. A clue that was hiding in plain sight for decades before anyone thought to use it the way it would eventually be used. The wall has no door, but the wall itself might move. Before we walk through the second theory, we need to sit with the first one a little longer, because special relativity says more than that you cannot reach light speed. It reveals something even stranger about what happens when you try. Something that would haunt every future mission planner who ever dreamed about the stars. Something called time dilation. Imagine your ship has solved the energy problem somehow. Ignore the infinite cost for a moment and picture a craft accelerating toward Proxima Centauri at a high fraction of light speed. Let us say you push the ship to 99.99% of light speed. The engines fire, and you begin the crossing. From inside the ship, the journey might feel like it takes a few weeks. Your biological clock, your aging process, the food you eat, the time you sleep, all of it would tick along normally from your perspective. You would age a few weeks. But the universe outside your ship would not agree with your clock. At that speed, time inside the ship runs at a drastically different rate than time outside it. While you age a month, Earth ages something closer to a century. The effect compounds as you climb toward light speed. A crew that departs Earth today might age 10 years on the voyage out and 10 years back, stepping off the ship roughly 2 decades older than when they left. The civilization they return to would be thousands of years ahead of the one that launched them. This is something Einstein's equations predict with precision, and it is something we have confirmed with real experiments. Atomic clocks flown on aircraft run slightly slower than identical clocks on the ground. The effect is small at airplane speeds, but it is real, and it matches the predictions exactly. At near light speed, the effect would be enormous. The crew would live full lives. They would sleep and eat and think and age, and they would return to an Earth that has moved on without them by thousands of years. You might look at that and think it sounds like a solution. The crew ages slowly while the universe rushes past them. But think about what you are really asking. You want to reach Proxima Centauri and come back. The whole point is to bring what you find there to the people who sent you. You want the mission to mean something to someone alive. Time dilation does not give you that. It stretches the crew's experience, but it does not shrink the objective distance. Everyone you left behind on Earth is dead when you return. The crew of this hypothetical mission are travelers who can never truly go home. The time dilation that lets them survive the journey is the same mechanism that severs their connection to every person they ever loved. That is a different kind of tragedy. So let us be honest about where we stand. Special relativity has built a box around us. You cannot reach light speed because the energy cost is infinite, and even if you get close, The universe around you will age and change at a rate that makes the journey a one-way ticket into the far future. But Einstein was not done. 10 years later, he returned to the problem with a larger set of tools, and in that second theory, he described something that special relativity had never touched: the behavior of space itself. In 1915, Einstein completed the general theory of relativity. It is, by most accounts, the most beautiful piece of physics ever written. It took him 10 years of grueling work, false starts, mathematical crises, and moments of nearly giving up. What he arrived at was a description of gravity so complete and so strange that it rewired how every physicist since has thought about the cosmos. General relativity says that space and time are not a fixed stage on which events occur. They are physical things. They can bend, stretch, compress, and curve. Mass and energy warp the fabric of spacetime, the way a heavy object warps a stretched rubber sheet. The planet orbiting our star is not being pulled by a mysterious force reaching across empty space. It is rolling along a curve in the space-time fabric that our star's mass has created. Gravity is geometry. This is the part that changes everything for the mission. In special relativity, the speed of light is the absolute limit for any object moving through space. Nothing with mass can move through space faster than light. But general relativity introduced something that special relativity never addressed: the motion of space itself. The fabric of space-time can move. It can expand, contract, and flow. And here is the key point, the one that physicists spent decades not quite fully applying to interstellar travel. The speed of light limit applies to objects moving through space. It does not apply to the motion of space itself. We know this from cosmology. The universe is expanding. Distant galaxies are receding from us at rates that, when you measure the velocity implied by their growing distance, exceed the speed of light. Not because those galaxies are moving through space faster than light, but because the space between us and them is stretching. The galaxies are not breaking the speed limit. The fabric they sit on is simply getting larger. The law is not violated because the law was never about the motion of space-time. It was about the motion of objects through space-time. This distinction is subtle, but it is the crack in the wall. The wall that special relativity built says you cannot move through space faster than light, but if space itself can move at any rate, with no apparent speed limit, then the question changes completely. Instead of asking how to push a ship faster through space, we should be asking something different. We should be asking whether there is a way to make space move around the ship. That reframing is not a philosophical trick. It is a genuine shift in the physics of the problem. Special relativity and general relativity are both true, and they govern different things. Put them together, and a possibility emerges that neither theory alone would suggest. A possibility that lay dormant in the mathematics for nearly 8 decades, until a young Mexican physicist decided to take it seriously. But before we get to that person, we need to understand what this loophole actually requires. Moving space itself is not a small ask. The question is whether the universe permits it in a controlled, local way. Whether space-time can be shaped not by the passive weight of planets and stars, but by something we design. The answer, at least mathematically, turns out to be yes. And the shape it takes is something genuinely strange. Let us try a picture. Take a rubber sheet and stretch it flat between your hands. Now, place a marble in the center. The sheet curves down around it. That curve is what general relativity means when it says mass warps spacetime. Every object with mass does this, including our star, including Earth, including you. You are bending spacetime right now by a tiny, unmeasurable amount, but bending it nonetheless. Now imagine the reverse. Instead of pressing down to create a curve, you could, in principle, create a shape that pushes a region of the sheet forward and lets a region behind it spring back, a ripple that moves across the rubber. The thing sitting inside that ripple does not move relative to the rubber directly beneath it. The rubber moves, and the thing rides it. The object itself is locally stationary. From inside the bubble of flat rubber, there is no acceleration, no force, no indication of motion at all, and yet the object has traveled. This is the conceptual heart of what we are building toward. A spacecraft that does not accelerate through space. A spacecraft that sits inside a region of space-time, and that region moves. The ship and its crew experience no thrust, no crushing g-forces, no relativistic effects. To them, they are simply sitting in a room. The room, however, is being carried across the universe by the shape of space itself. The objection you might have right now is that this sounds like cheating. You are right that it sounds that way, but cheating implies breaking the rules. Nothing in what we just described breaks any law of physics. Special relativity forbids objects from moving through space faster than light. It says nothing about space-time itself being reshaped in a way that carries an object from one point to another. The rules were written for a static stage. We are proposing to move the stage. Think about what the traveler inside this bubble would experience. No acceleration. No time dilation relative to the outside universe, because the ship is not actually moving fast through space. The clock inside the bubble ticks at the same rate as the clock back on Earth. The crew ages at the normal human rate. They arrive at Proxima Centauri, having spent whatever journey time the bubble configuration requires. And when they return, everyone back home has aged by roughly the same amount. This is a genuine two-way journey. The elegance of this idea is almost unsettling. Every objection that haunted near lightspeed travel, the infinite energy cost, the time dilation, the causality problems for the crew, simply does not apply here. Those problems were problems of moving through space. We are proposing to move space. Different rules. Of course, a rubber sheet analogy only takes you so far. The universe is not actually rubber. Warping space-time in the way we are describing requires something real, something physical, something that can actually produce this geometry. And that is where the story gets harder and more interesting, and where a specific human being, sitting at a desk in Mexico in the early 1990s, decided to write down the equation that describes exactly what this shape would look like. He had a television show in mind when he started, and what he ended up writing would be read and argued over and built upon by physicists for the next 3 decades. In 1994, a Mexican physicist named Miguel Alcubierre was finishing his graduate work in Wales. He was thinking about Star Trek. Specifically, he was thinking about the warp drive that the fictional starship Enterprise used to travel between star systems in hours instead of centuries. Most physicists dismissed the concept as pure fantasy, a storytelling device, the kind of thing science fiction invents because real physics gets in the way of a good narrative. Alcubierre decided to ask a more precise question. He wanted to know whether there was any configuration of space-time geometry that would allow faster-than-light travel without violating general relativity. He was not asking whether we could build it. He was asking whether it was mathematically consistent with the laws of physics as we know them, whether the equations of general relativity, which describe how space-time can be shaped and curved, permitted any solution that would allow a spacecraft to arrive at a destination faster than a light beam could travel through flat, unmodified space. He found one. The paper Alcubierre published that year is not long. It is precise and mathematical, written in the austere language of theoretical physics. But what it describes is genuinely startling. He showed that general relativity permits a specific shape of spacetime, a geometry that creates a region in front of a spacecraft where space is compressed and a region behind where space is expanded. The spacecraft sits inside a flat bubble between these two distortions. The bubble itself moves. The ship inside the bubble stays locally at rest. The mathematics showed that an observer inside this bubble would travel between 2 points in less time than it would take light to cover the same distance through undistorted space, all without the ship itself ever exceeding the speed of light locally. all without any violation of Einstein's equations. The geometry was legal. The space-time shape was permitted by the same laws that govern black holes and gravitational waves and the expansion of the universe. The concept is now known as the Alcubierre warp drive, or the Alcubierre metric, and it launched a debate in theoretical physics that has not stopped. Some physicists celebrated it as the first mathematically rigorous proposal for faster-than-light travel. Others raised immediate objections, pointing to deep problems with the physics required to produce such a geometry. But almost everyone agreed on one thing. The question Alcubierre had asked was worth asking, and the answer he found deserved serious examination. What Alcubierre did was something rare in the history of the field. He did not invent a new law. He did not overturn existing physics. He read the existing laws more carefully than anyone before him and found permission where others had seen only prohibition. He asked general relativity a question it had never been asked, and the equations answered yes. For our mission, this moment matters enormously. Before 1994, faster-than-light travel existed only in the pages of science fiction novels and on television screens. After that paper, it existed in a peer-reviewed physics journal. That is a different kind of existence entirely. The engineer in you is already asking whether we can build it. The physicist in you is asking how it works. And the answer to the second question is the only path to the first. Picture your spacecraft. It is sitting in ordinary, flat spacetime, the way all objects sit in space when nothing unusual is happening nearby. Now imagine that the space-time fabric directly ahead of the ship begins to compress. The space in front of you is getting smaller, the distance to your destination shrinking. Simultaneously, the space-time behind the ship begins to expand. The space you just left is stretching out, growing larger, pushing the region you came from further away. The ship itself does nothing. It fires no engines. It applies no thrust. It simply sits in a region of space-time that remains flat and undisturbed, a bubble of normal space carried between the compression ahead and the expansion behind. From inside the bubble, you feel nothing. There are no g-forces because you are not accelerating through space. Your instruments read normal. You could pour a cup of coffee and the liquid would sit flat in the cup. Nothing about your immediate environment suggests you are moving at all. But from outside, from the perspective of the universe around the bubble, your effective velocity is extraordinary. The compression of space ahead of you has reduced the distance to your destination. The expansion behind has increased the distance from your origin. The bubble is closing the gap between where you started and where you are going, and it is doing so at a rate that, depending on how aggressively you shape the geometry, can exceed the speed of light. The ship is always at rest inside its bubble. The bubble moves. These are two different things, and the distinction is the difference between what special relativity forbids and what general relativity permits. Special relativity forbids a massive object from moving through space faster than light. General relativity says the shape of space itself can evolve and flow. The Alcubierre geometry uses this permission. Every part of the ship's journey is locally subluminal. Globally, the trip is faster than light. The bubble also protects the crew from one of the most dangerous hazards of near-light speed travel: particle bombardment. At high fractions of light speed, even the thin gas and dust of interstellar space becomes a lethal radiation storm hitting the front of the ship. Inside the warp bubble, you are not moving through that material. The space at the front of the bubble is compressing, and the particles that might otherwise hit the ship are being moved around and accumulated at the boundary. The crew inside is shielded not by armor but by geometry. This is what makes the Alcubierre metric so compelling to physicists and mission planners alike. It addresses multiple problems at once. It bypasses the infinite energy cost of near-light acceleration. It eliminates time dilation for the crew. It provides natural shielding from interstellar medium. And it does all of this by working with the laws of physics, not against them. The question that follows immediately is the one that has occupied every researcher who has touched this subject since 1994. If the geometry is legal, if the math checks out, what does it actually take to create the bubble? What physical process, produces the space-time compression ahead and the expansion behind? The answer to that question reveals why this mission, despite being mathematically permitted, faces an obstacle that makes the fuel problem of conventional rockets look trivial by comparison. When Alcubierre published his paper, he described the shape of the warp bubble and then calculated what it would actually take to create one. To bend space-time in the way the metric requires, to compress space ahead and expand it behind on the scale needed to carry a spacecraft, you need a source of energy that does not behave like ordinary matter or ordinary energy. You need something with what physicists call negative energy density. Something that pushes space-time outward rather than pulling it inward. This sounds exotic. It is exotic, but it is not without precedent in physics. The Casimir effect, a measurable phenomenon in quantum mechanics, demonstrates that negative energy can exist between closely spaced conducting plates in a vacuum. Two metal plates, placed almost touching in empty space, create a region between them where the energy density drops below zero. The effect is real, observed in laboratories around the world, and consistent with quantum field theory. Negative energy is not forbidden by the universe. It exists. What matters for the mission is how much of it the warp bubble requires. Alcubierre ran the numbers. The original calculation was staggering. To create a warp bubble large enough to carry a spacecraft, say a bubble roughly 300 feet across, the amount of negative energy required was approximately equal to the total mass energy of the planet. Jupiter converted entirely into its exotic equivalent. That is the energy content of a planet with a mass of more than 300 Earths, converted to negative form and deployed in a precise geometric shell around the ship. Let that settle for a moment. Jupiter has a mass of roughly 4 quadrillion pounds. Converting that entire mass into energy, following the equation that connects mass and energy, produces a number so large it resists ordinary language. And the warp bubble needed all of it, in negative form, concentrated in a thin shell of exotic matter surrounding the spacecraft. Every last fraction of it, arranged with perfect precision, just to carry one ship across the stars. When other physicists saw this number, many of them considered the case effectively closed. The geometry might be mathematically legal, but the energy requirement placed it beyond any conceivable physical means. We cannot even measure, let alone produce, Jupiter mass quantities of exotic negative energy. The gap between what the math requires and what the universe seems willing to provide was not a gap you could engineer your way across. It was not even a gap in the usual sense of the word. It was a chasm so wide it made the original distance to Proxima seem almost modest by comparison. But here is the thing about theoretical physics. The initial calculation is rarely the final word. The history of the field is full of problems that looked fatal until someone found a smarter geometry, a more efficient configuration, a different way of achieving the same result with less. Alcubierre had asked whether the shape was allowed. He proved it was. The next question, the one that would drive the field for decades, was whether there was a smarter version of that shape, one that cost less, one that brought the bill down from impossible to merely extraordinary. And the first person to find a way to shrink it was already reading the paper. 5 years after Alcubierre's original paper, a Belgian physicist named Chris van den Broek published a modification that changed the numbers significantly. Van den Broek looked at the geometry of the warp bubble and asked a question that seems obvious in hindsight. Does the size of the space the bubble needs to warp have to correspond directly to the size of the space the ship occupies? Alcubierre's original design created a large flat region inside the bubble because the ship needed room to exist. That large flat region required a proportionally large amount of exotic matter to maintain its geometry. More room inside meant more exotic matter in the walls. Van den Broek proposed a trick. What if the inside of the bubble was structured differently from the outside? What if the flat region where the ship actually sits could be enormous in terms of interior volume, but tiny in terms of the external bubble wall that has to be maintained by exotic matter? In other words, what if the geometry of the bubble was designed so that the ship occupied a large internal space that opened out from a very small external mouth. This sounds counterintuitive, but general relativity actually permits it. The topology of spacetime can be arranged so that a small opening connects to a much larger interior, the way a doorway might be narrow while the room behind it is vast. Van den Broek used this mathematical freedom to design a bubble whose exterior wall, the part that requires exotic matter to hold in place, was dramatically smaller than the habitable space inside it. The result was a reduction in the required exotic matter by many orders of magnitude. Instead of Jupiter's mass energy, the Van den Broek modification brought the requirement down to roughly the mass energy of our star, a solar mass of exotic energy. This was still an absurdly large number, still impossibly far from anything we could produce or even conceive of producing with foreseeable technology. But the direction of travel mattered enormously to the physics community. The original Alcubierre requirement had felt like a dead end. Van den Broek's reduction showed that the number was not carved into the foundations of reality. It was a function of the geometry, and the geometry had room to be optimized. If one clever modification could reduce the cost by many orders of magnitude, further refinements might reduce it further still. The scientific community did not declare victory, but they did not quit either. They kept negotiating with the equations, kept probing the geometry for inefficiencies, kept asking whether the shape could be made cheaper. What Van den Broek demonstrated was that the energy problem was a design problem, not a fundamental prohibition. The universe was not saying you cannot do this no matter what. It was saying your current design is wasteful. Fix the design. And as the 1990s turned into the 2000s and then the 2010s, a small but serious community of physicists kept working on exactly that question, kept asking whether there was a configuration that brought the energy requirement within the realm of something a civilization might one day produce. One of those people worked in a building with a very particular name on the door, and when he published his results, the conversation about warp drives stopped being purely academic. In the fall of 2011, a physicist at the Johnson Space Center in Houston named Harold White, known to his colleagues as Sonny, stood up at a conference and presented a calculation that made the room lean forward. White was not a fringe researcher posting on the internet. He worked for the National Aeronautics and Space Administration inside a small advanced concepts group called EagleWorks. The group existed to explore propulsion physics that sat at the outer boundary of what the field currently understood. Sonny White had been thinking about the Alcubierre warp drive problem for years, and he believed the energy numbers could be pushed dramatically lower. His modification to the Alcubierre geometry introduced an idea that had not been fully explored before. Instead of a static bubble, a fixed shell of exotic matter holding its shape indefinitely, White proposed a bubble that oscillated. The shell of exotic matter surrounding the ship would pulse, changing its shape dynamically rather than holding a rigid configuration. White argued that this oscillating toroidal shape, a bubble that varied its geometry over time in a ring-like pattern, would be significantly more energy efficient than any static design previously analyzed. When White ran the numbers using his modified geometry, the result was dramatically different from anything that had come before. He claimed that the exotic matter requirement for an Alcubierre-style warp field might be reduced to roughly the equivalent of 700 kilograms of mass converted to exotic energy. 700 kilograms. That number should stop you cold. The requirement had gone from the mass energy of Jupiter to the mass energy of our star to something that weighs less than a small car, an amount that does not require harvesting any astronomical body. The physics community responded with immediate interest and immediate skepticism in roughly equal measure. Interest, because the direction of the reduction was consistent with the pattern Van den Broek had established, and because the magnitude, if correct, would represent a qualitative change in what was worth taking seriously. Skepticism, because White's calculation relied on assumptions about the oscillating geometry that had not been fully vetted, and because extraordinary claims in theoretical physics require extraordinary peer scrutiny before they earn acceptance. White went further than numbers on a page. He proposed and partially set up a small laboratory experiment at Eagleworks, using an instrument called a White-Juday warp field interferometer, designed to detect whether a toroidal ring of test material could create a measurable, if tiny, distortion in spacetime. The experiment never produced a confirmed signal at the scale needed to validate the concept. The peer review of White's energy calculations remained incomplete and contested in subsequent years. He eventually left the Eagleworks program, and the experimental work did not continue in the form he had proposed. But something had changed regardless. A physicist employed by the agency that put human beings on the moon had taken the Alcubierre metric seriously enough to build laboratory equipment around it. The conversation had shifted from pure theory into something that occupied a complicated, contested space between speculation and early-stage experimental research. And the question White's work left hanging over the field is the one researchers are still chasing today. If the energy requirement can fall from Jupiter to a star to 700 kilograms through successive geometric refinements, where does that curve end? Is there a flaw? And what happens if there is not? The Alcubierre metric is a valid solution to Einstein's field equations. That much is settled. The mathematics holds, the geometry works, and the theoretical framework for warping space-time around a craft has survived decades of peer review. What the same mathematics also tells you, with the same precision, is the price. And the price is staggering in a way that stops most conversations cold. To warp space-time the way Alcubierre described, you need matter with negative energy density. Every form of ordinary matter you have ever encountered carries positive energy. Compress it, heat it, accelerate it, and the energy content rises. There is no natural process that drives matter's energy below zero in the way the Alcubierre metric demands. The requirement is not for a small exotic fuel source tucked into a corner of the spacecraft. The geometry of the warp bubble requires negative energy threaded throughout the shell itself, woven continuously into the fabric of the curvature that drives the bubble forward. When physicists first tried to calculate how much exotic matter a working drive would require, the figures came back in units that should make anyone pause. Miguel Alcubierre's original 1994 paper implied that you would need something on the order of the mass energy equivalent of Jupiter, expressed as negative energy. That number arrived from the most straightforward reading of the geometry. Later refinements reduced the estimate considerably, but those reductions came from increasingly specific geometric choices, thinner bubble walls, and adjusted curvature profiles. Each revision traded one set of problems for another. Even the most optimistic modern estimates require exotic matter, measured in quantities that dwarf anything humanity has ever manufactured or detected. Here is where the physics community reaches a critical fork. Exotic matter with negative energy density is permitted by general relativity. The equations do not forbid it outright. The problem is that no laboratory has ever produced it in meaningful quantities, and there are deep theoretical reasons to suspect that nature imposes hard limits on how much negative energy can exist in any region of space. The relevant constraints are called quantum energy conditions. Classical physics banned negative energy outright, treating it as unphysical. Then, quantum mechanics arrived and complicated the picture considerably. Quantum fields can briefly dip below zero energy in localized regions, which opened a door. But those dips appear tightly constrained by inequalities studied extensively since the 1980s. Lawrence Ford and Thomas Roman developed the key versions of these constraints, and their analysis suggested a fundamental trade-off. The more negative the energy density you try to achieve, the shorter and smaller the region in which you can sustain it must be. Push harder on the negative side, and the geometry of the constraint snaps back with equal force. These Ford-Roman inequalities do not absolutely prohibit the exotic matter an Alcubierre drive requires. What they do is make it extraordinarily difficult in practice. A device producing significant negative energy density would need to confine it in a vanishingly brief duration or a microscopically thin region. and the total negative energy available at any moment would be far too small to curve space-time on any useful scale. What you are left with is a beautiful geometric solution wearing an impossible price tag. The space-time warping works on paper. The fuel does not exist in the universe in the required form. Physicists began searching not to prove the drive impossible, but to find any foothold in known physics where negative energy had actually been confirmed. They found one. It was thinner than a human hair. It involved two metal plates and a quantum prediction from 1948, and it was entirely real. In 1948, a Dutch physicist named Hendrik Casimir made a prediction that seemed almost too strange to take seriously. If you took two flat, uncharged metal plates and positioned them parallel to each other in a perfect vacuum, separated by a gap of only a few nanometers, something would happen that classical physics had no language to describe. The plates would attract each other, nothing would be touching them, no charge, no gravity at that scale, no magnetic field. And still, they would draw together. The mechanism Casimir identified was quantum in nature. According to quantum field theory, empty space is never truly empty. The vacuum seethes with fluctuating energy fields, virtual particles blinking in and out of existence too quickly to be measured directly, but real enough to carry force. Outside the gap between the plates, these quantum fluctuations fill all of space across the full range of wavelengths they can occupy. Inside the gap, only wavelengths short enough to fit between the plates are permitted. The restriction is geometric, a consequence of the plates serving as physical boundaries. The result is a difference in energy density. Outside the gap, the vacuum energy is higher. Inside, it is lower. Measurably, verifiably lower. That is the Casimir effect. The plates press together because the space between them contains less vacuum energy than the space outside them, and that difference in energy density pushes them inward with a measurable force. When you stop and consider what this means for the exotic matter problem, the implications take a moment to arrive. The space between the Casimir plates has a negative energy density relative to normal empty space. The quantum vacuum between those plates sits below the baseline energy of the ordinary vacuum. This is, by every rigorous definition, the exotic matter state the Alcubierre metric requires. Negative energy density, achieved in a real laboratory, confirmed by experiment, and consistent with every known law of physics. The first experimental confirmation of the Casimir effect came in 1958, and the measurements have grown only more precise since then. Stephen Lamoureux provided the first highly accurate experimental verification in 1997, and subsequent measurements have matched the theoretical predictions to within a fraction of a percent. The effect is real. The negative energy is real. The question that follows is whether this foothold is usable, and this is where the enthusiasm runs into a wall. The Casimir effect produces negative energy in the space between plates, separated by distances measured in nanometers, roughly 1/10,000th the width of a human hair. The magnitude of the negative energy density scales inversely with the fourth power of the plate separation. Move the plates apart by a factor of 10, and the effect drops by a factor of 10,000. The amount of negative energy produced is unmeasurably small by macroscopic standards, far below anything that could curve spacetime in any detectable way. To produce the negative energy required by even the most optimistic revised estimates for the Alcubierre drive, you would need Casimir-like geometries operating across scales, and in configurations that bear no resemblance to anything physically constructible with current technology, or any technology on the foreseeable horizon. And yet, the Casimir effect matters enormously in this conversation, because it closes a theoretical escape route. Critics who argued that negative energy was simply impossible now had to contend with a laboratory that had measured it. The exotic matter requirement moved from impossible to merely extraordinary. That distinction, narrow as it sounds, would matter to every researcher who came after. Imagine you are aboard the craft inside a working Alcubierre warp bubble. The space-time around you has been distorted precisely as the mathematics describes. Compressed ahead, stretched behind, the bubble carries you through the cosmos at effective multiples of the speed of light, while you yourself remain stationary relative to the space immediately surrounding you. The journey to Proxima Centauri might take days rather than 4¼ years. From the outside, this is extraordinary. From the inside, the picture becomes considerably darker. The warp bubble is not a ship. It is a region of space-time that has been sculpted into a specific geometric shape. You exist inside that region, untouched by the forces driving it, a passenger inside a wave rather than someone swimming through water. The critical consequence of this arrangement is that the bubble's walls are, by definition, moving away from you at superluminal speeds in every direction. The leading edge of the bubble contracts space faster than light crosses it. The trailing edge expands space faster than light can traverse it. Every boundary of the structure that protects and propels you is, from your perspective, inside the bubble, unreachable. This creates a problem so fundamental it threatens the entire concept. If you want to send a signal to the bubble wall, perhaps to adjust it, to steer it, to slow it, that signal must travel from your position inside the bubble to the boundary. But the boundary is receding or advancing faster than any signal you can generate. Light itself cannot reach the leading wall. Instructions transmitted at the speed of light would chase the front edge forever without catching it. The information you send backward toward the trailing wall would never arrive because the expansion behind you is equally unreachable from within. In technical language, the interior of an Alcubierre warp bubble lies within its own causal boundary. Events inside cannot causally affect events on the wall. The crew is, in a precise and inescapable sense, imprisoned. This causal severance is not a design flaw that better engineering could correct. The geometry itself prevents it. The same superluminal expansion and contraction of space that makes the bubble useful is the geometry that severs communication between the interior and the boundary. The two conditions are inseparable. A functional Alcubierre bubble and a causal link from inside to outside cannot coexist. The practical implications are severe. Steering requires communication with the boundary. Stopping requires collapsing the bubble. If neither can be achieved from inside, then an Alcubierre drive, once engaged, is committed to its destination, whether the crew wishes to stop or not. Any obstacle in the path cannot be addressed by anyone inside. Any navigation correction the crew identifies becomes irrelevant the moment the bubble is active. Some physicists have pointed out that the bubble could theoretically be pre-programmed before departure, its entire trajectory calculated and encoded into the initial conditions. A sufficiently precise computation of the route, accounting for every gravitational influence along the way, would eliminate the need for real-time correction. The bubble collapses at the programmed endpoint and nowhere else. The stars between here and Proxima Centauri are not surrounded by empty space. However, interstellar space contains dust, gas, and magnetic fields. A pre-programmed bubble navigating 4 light-years of real interstellar medium without adjustment is navigating blindly, and the passengers inside it cannot do anything about what they find along the way. The causal disconnect inside the warp bubble looked, at first glance, like a complete shutdown of the concept. If the crew cannot communicate with the bubble wall, and the wall cannot be steered or stopped from inside, then the drive becomes a guided projectile that nobody can guide. Physicists who took the problem seriously, rather than treating it as a reason to abandon the idea, began looking for ways around it. The most straightforward workaround is pre-programming. Before departure, the bubble's trajectory is calculated with enough precision to encode the entire journey, including the moment and method of collapse at the destination. The crew does not steer in flight because all steering decisions were made before the bubble ever engaged. Think of it less like piloting an aircraft and more like programming a ballistic trajectory from the ground before launch. The calculation must account for every significant gravitational influence between origin and destination, every dense gas cloud, every stellar mass in the vicinity of the path. For a journey to Proxima Centauri, 4.25 light-years away, the relevant gravitational fields are relatively well mapped. The void between our star and its nearest neighbor is not as empty as intuition suggests, but it is not densely populated either. A sufficiently sophisticated simulation of the route, built from comprehensive astronomical surveys of the path, could in principle encode a pre-programmed collapse that lands the bubble at the target and releases its passengers. The crew would simply wait, unable to intervene, trusting a navigation calculation made days or years before they arrived. That solution sounds manageable until you consider what quantum mechanics has to say about it. Several physicists, including William Unruh and others working at the intersection of quantum field theory and curved spacetime, have raised the possibility that quantum effects inside the warp bubble may not behave as classical calculations predict. The bubble wall is a region of intense spacetime curvature. Quantum fields respond to curvature in ways that can produce radiation, particle pairs, and energy fluctuations that classical general relativity does not anticipate. The Hawking radiation produced at black hole horizons is the most famous example of this phenomenon, and the Alcubierre bubble has geometric features that share some properties with event horizons. If quantum effects destabilize the bubble wall, then pre-programming solves the wrong problem. The question becomes not only where the bubble goes, but whether it holds together during the journey. A bubble that radiates energy from its walls, or that experiences quantum-driven fluctuations in its curvature, may collapse prematurely or collapse unevenly in ways that the pre-programmed trajectory cannot accommodate. A second theoretical approach involves cascading architectures. Rather than one continuous warp bubble maintained for the duration of the trip, a cascade design would create a series of smaller, shorter duration bubbles, each one collapsing and reforming in rapid sequence along a predetermined path. Each individual bubble in the chain would be smaller and simpler than a single journey-length bubble, potentially reducing the exotic matter requirements at each stage. The overall journey would resemble a series of short quantum hops rather than one sustained superluminal flight. Whether cascading architectures actually resolve the causal communication problem depends on the transition mechanics. Between bubbles, a regime where the physics is particularly uncertain, each workaround opens a new set of questions. The drive that seemed clean on paper, a smooth, geometric wave carrying a spacecraft to the stars, reveals more texture and complication at every level of scrutiny. But each question also implies a direction for further investigation. And while physicists wrestled with the internal mechanics of Alcubierre's bubble, a Soviet researcher had been thinking about a different approach altogether. Sergei Krasnikov was not trying to solve the same problem Alcubierre had solved. By 1995, the warp bubble was already established in the literature as a theoretically permitted spacetime geometry, with an exotic matter problem, a causal communication problem, and a host of other complications. Krasnikov's starting point was different. He wanted to know whether faster-than-light travel between two fixed points could be possible if you thought about the problem from a different angle entirely. His proposal described something now called the Krasnikov tube. The concept begins with a spacecraft that does not warp space around itself. Instead, the ship travels outward from its home star toward a destination at a speed below the speed of light, and as it travels, it permanently modifies the causal structure of spacetime behind it. The modification is not a bubble that moves with the ship. It is a corridor of altered spacetime stretching between the departure point and the destination, left behind as a permanent feature of the geometry. The ship's first journey is, in this respect, entirely conventional. It covers 4.25 light-years at sublight velocity, taking years to arrive. Nothing about the outward journey exceeds the cosmic speed limit. The modification happens gradually. In the wake of the ship, as a side effect of the drive mechanism rather than its primary mode of propulsion. What changes everything is the return trip. The tube the ship has left behind does not simply connect the 2 points across ordinary space. It connects them across a modified space-time in which the causal structure has been rearranged. The tube allows a signal, or a ship, to travel from the destination back to the home star at an effective speed exceeding the speed of light, without violating the local speed limit at any point inside the tube. Inside the tube, nothing travels faster than light locally, but the tube itself has been shaped so that the path from destination to origin covers an enormously shorter space-time interval than the path outside it. The return journey through the tube takes far less time than the outbound journey did. This is a fundamentally different architecture from Alcubierre's, where Alcubierre warped space into a moving bubble that carried the ship inside it. Krasnikov created a persistent infrastructure, a modification to the universe's geometry that remained in place and could be used repeatedly. Once the tube existed, any subsequent ship could use it. Communication could be sent through it. The investment in the first journey would pay dividends for every journey after. The geometry Krasnikov described shares some of the mathematical elegance of the warp bubble. Like the bubble, it satisfies Einstein's field equations, at least in principle. Like the bubble, it exploits the flexibility that general relativity allows in space-time geometry without requiring any object to travel faster than light in its local frame. The relativistic mechanism that makes the journey work is in the shape of the space-time, not in the velocity of anything moving through it. The proposal attracted serious attention. Here was a scenario in which the first expedition to a nearby star, launched at sublight speed with conventional propulsion, would permanently build the infrastructure for all future faster-than-light communication with that star system. One generation of explorers, traveling slowly, would pave the way for every generation after to travel fast. The mathematics checked out. The concept was coherent. There was a catch. The Krasnikov tube has a catch built into its own logic, and it shows up before you even begin calculating the exotic matter requirements. The problem is right there in the most appealing feature of the concept. The first journey takes the full travel time at sublight speed. Proxima Centauri is 4.25 light years away. A ship traveling at 90% of the speed of light would reach it in roughly 4 years and 9 months by the clocks of observers back home, with time dilation reducing the subjective journey time for the crew aboard. A ship traveling at a more realistic fraction of the speed of light might take decades. In every version of the Krasnikov tube scenario, the first expedition is a generational sacrifice. The people who build the tube do not benefit from it. They travel slowly, arrive after years or decades, and leave behind an infrastructure they will never personally use to come home quickly. This is a genuine limitation, not a temporary engineering obstacle. The tube does not exist until the first ship creates it. The first ship cannot use it because it is in the process of creating it. Any scheme to use Krasnikov tubes for faster-than-light travel requires accepting that the first link in the chain costs the full sublight travel time. The benefit accumulates only from the second voyage onward. For a civilization planning decades or centuries into the future, this may be acceptable. For anyone hoping to use the tube personally, the first trip problem is a fundamental barrier. The second catch is the familiar one. Krasnikov tubes, like the Alcubierre bubble, require exotic matter with negative energy density to maintain their structure. The mathematics of the tube's causal modification demands that the corridor through which faster-than-light return travel occurs be threaded with negative energy in the walls of the tube. Without that exotic matter, the tube cannot maintain the space-time geometry that makes the return journey superluminal. The tube would collapse back into ordinary space-time, and with it the accumulated advantage of the first expedition. The exotic matter problem that plagued the Alcubierre drive shows up again here, wearing a different geometric costume. The shapes are different, the curvature profiles are different, The physical arrangement of the structure is entirely different, but the underlying requirement is identical. Somewhere in the construction, there must be matter whose energy density is negative in a region where ordinary matter cannot go negative. There is an additional complication that Krasnikov himself and later researchers identified. When physicists examined what happens to two Krasnikov tubes pointing in opposite directions between the same pair of stars, the causal structure of the combined system becomes dangerous. The interaction of two tubes creates conditions that appear to allow closed time-like curves, paths through space-time that loop back on themselves in time. A traveler following a closed time-like curve could, in principle, arrive before they departed. The appearance of potential time travel was enough to trigger serious scrutiny about whether the tubes could be physically realized at all, or whether some deeper principle of physics would prevent their formation. The exotic matter requirement and the time travel complications placed the Krasnikov tube in a category that was beginning to feel familiar. Theoretically compelling, mathematically consistent, physically obstructed at every turn by the same recurring obstacle. And yet physicists kept searching, because there was another class of solution altogether, one that predated both Alcubierre and Krasnikov by decades, and one that Einstein himself had put his name on. In 1935, Albert Einstein and Nathan Rosen sat down together at the Institute for Advanced Study in Princeton and published a paper that tried to do something that had never been done before. They were working on a problem in quantum mechanics that had been bothering Einstein for years: the question of whether quantum particles could be understood as geometric features of space-time rather than as separate objects added onto it. The paper they produced took general relativity to a logical extreme, and buried in the mathematics, almost as a footnote to a different argument, was a structure that would take half a century to develop into one of the most discussed concepts in theoretical physics. Einstein and Rosen showed that if you write down the exact mathematical description of a black hole using the Schwarzschild solution to Einstein's field equations, and then examine that solution with complete care, there is a surprise in the geometry. A single maximally extended Schwarzschild black hole does not describe a one-ended funnel into infinite density. It describes two separate regions of spacetime, two exterior universes, connected by a narrow throat. The throat connects the two regions at a single point in their shared geometry. Einstein and Rosen called this structure a bridge. Later physicists would call it a wormhole. The physical picture is striking. Take two sheets of flat spacetime, representing two distant regions of the same universe, and bend them until they nearly touch. Then punch a hole through both and connect the two holes with a tube. That tube is the Einstein-Rosen bridge. Spacetime on one side connects to spacetime on the other through a passage that bypasses the ordinary distance between the two regions. The journey through the bridge could, in principle, take far less time than the journey around it through normal space. The concept captured the imagination of anyone who thought seriously about what spacetime could do. If such a structure existed naturally, or could be created artificially, it would provide a shortcut through the cosmos of exactly the kind that science fiction had always imagined. 2 points separated by millions of light years could be connected by a tunnel a few miles long. Travel that would take geological timescales at sublight speed could take minutes. There was a devastating problem, however, and Einstein and Rosen recognized it immediately. The bridge they had discovered was not a stable structure. In the original Schwarzschild solution, the throat of the Einstein-Rosen bridge is dynamic. It forms and collapses faster than any signal, even a light signal, can traverse it. The bridge opens and closes in a time so short that no physical object could pass through before it pinches off. It is a genuine geometric feature of the solution, but it is not a passageway. For the next several decades, the Einstein-Rosen bridge remained a mathematical curiosity rather than a physical proposal. Physicists would refer to it occasionally, examine its properties, and move on. The structure was real in the equations. The structure was useless in practice. What the bridge needed, someone eventually realized, was not a new solution, but a new question. Instead of deriving the bridge from existing solutions and then asking whether it was traversable, what if you started with traversability as the requirement and then asked what the bridge would have to look like? In 1988, Kip Thorne was one of the most respected relativists alive. He had spent decades working on the mathematics of black holes, gravitational waves, and the deep structure of spacetime. He was not, by temperament, someone who chased speculative ideas for their own sake. When a colleague asked him to examine the concept of traversable wormholes for the purpose of a science fiction novel, Thorne took the request more seriously than the occasion demanded. He sat down with his student Michael Morris, and they approached the problem from an unusual direction. Rather than starting with a known solution to Einstein's equations and asking whether it permitted traversal, they started with the traveler's requirements and asked what the geometry would have to be. What conditions must a wormhole satisfy if a human being were to pass through it alive? What would space-time look like at the throat? What forces would the traveler experience? What would the tidal effects be? They worked backward from the physics a person could survive and derived the geometry from those constraints. The result was the Morris-Thorne wormhole, published in the American Journal of Physics in 1988, in a paper now regularly cited as one of the most careful treatments of faster-than-light spacetime geometry in the literature. The paper was explicitly pedagogical, written to teach students how to think through the physics of exotic spacetime solutions, and yet it contained genuinely new results. Morris and Thorne showed that a traversable wormhole, one in which a human traveler could enter one end and exit the other without being shredded by tidal forces, stretched by spaghettification, or burned by intense radiation, was mathematically consistent with general relativity. The geometry they derived was smooth, the tidal forces were manageable, and the two mouths of the wormhole could in principle be positioned anywhere in the universe, connecting them across arbitrarily large distances. The paper also showed, with complete clarity, what such a wormhole required in order to remain open. A wormhole throat, unlike the static geometry of the Einstein-Rosen bridge, needs active support. Without something holding the throat open, the geometry collapses under its own gravitational dynamics, faster than any traveler could pass through. The something required to hold it open is, inevitably, matter with negative energy density. Exotic matter again. The same requirement that haunted the Alcubierre drive, the same requirement that the Casimir effect had demonstrated in miniature, showed up in the throat of every traversable wormhole as an inescapable structural necessity. Thorne did not treat this as a reason to abandon the concept. He treated it as a physics problem to be solved. If exotic matter was required, the question was, how much, in what geometric configuration, and whether quantum field theory could be called upon to supply it. The Casimir effect had already shown that quantum fields could produce negative energy density in controlled geometries. The question was one of scale. Morris-Thorne wormholes are ruled out by no known law of physics. They require exotic matter in quantities and configurations that far exceed anything available to current civilization. But their existence in the solution space of general relativity means they belong in the same category as Alcubierre bubbles and Krasnikov tubes. Permitted by theory, obstructed by practice, and worth continuing to examine. There was one more obstacle waiting, and it was about size. If wormholes exist in nature, no astronomer has ever seen one. The universe at the scales visible to telescopes shows no evidence of stable, traversable throats connecting distant regions of spacetime. If they form naturally, they do so somewhere far below the threshold of any instrument ever built. Theoretical physicists who have thought carefully about when and how wormholes might form have arrived at a number that puts the entire enterprise in a sobering light. The relevant scale is the Planck length, named for Max Planck, who identified it from the fundamental constants of nature at the turn of the 20th century. The Planck length is the distance at which quantum gravitational effects become dominant, the scale at which the smooth geometric description of space-time breaks down, and something more fundamental would be needed to describe what happens. The Planck length is approximately 1.6 times 10 to the power of negative 35 meters. Written in full, that is a decimal point followed by 34 zeros and then 16. The width of a proton, one of the smallest physical objects with a well-defined size, is approximately 1 femtometer, which is 10 to the power of negative 15 meters. The Planck length is smaller than a proton by a factor of roughly 10 to the 20th power, meaning the Planck length is 100 billion times smaller than a proton. The ratio of a proton to the Planck length is comparable to the ratio of the entire visible universe to a proton. It is a scale so distant from ordinary physical reality that no experiment in the foreseeable future will probe it directly. Wormholes that form naturally are expected to exist at or near the Planck scale. Quantum foam, the name physicists give to the hypothesized turbulent structure of spacetime at these lengths, may contain a seething topology of tiny wormholes forming and collapsing on timescales measured in Planck time, roughly 5 times 10 to the power of negative 44 seconds. These structures, if they exist, are smaller than the nucleus of an atom by a factor that exceeds comprehension. They are not simply small obstacles to overcome with better engineering. They exist in a regime where the engineering language of this era has no meaning. To make a wormhole traversable by a human being, or even by a single proton, it would have to be expanded from Planck scale to at minimum atomic scale, a factor of roughly 10 to the 20th in size. To make it traversable by a spacecraft, it would need to be expanded by a further factor of roughly 10 to the 35. The total expansion required is a factor of approximately 10 to the 55, a 1 followed by 55 zeros. Nobody has a theory for how to accomplish this. The energy required, even in the most optimistic estimates, would be astronomical in the literal sense, comparable to the energy output of stars over geological timescales. And all of this assumes Planck-scale wormholes exist in the first place, which remains a theoretical conjecture rather than an established physical observation. The scale problem does not make traversable wormholes impossible. It makes them so far from practical reality that the gap between theory and engineering is not a matter of decades or centuries, but of orders of magnitude that have no precedent in the history of technology. The dream persisted anyway, because elsewhere in physics, a different kind of shortcut had appeared, one that operated at scales humans could actually measure. Quantum entanglement is the strangest confirmed fact in all of physics. Two particles, prepared together in a specific quantum state, share a connection that persists regardless of the distance between them. Measure a property of one particle and the other particle, wherever it is in the universe, will display a correlated property instantaneously. The correlation appears before any signal could travel between them. It behaves as though the two particles remain in contact across any separation. No matter how vast, the phenomenon is real. It has been confirmed in laboratories hundreds of times, with separations that have grown from centimeters to kilometers to over 1,000 miles in satellite experiments conducted in the last decade. The correlation is genuine, not a statistical artifact, not a result of hidden variables that both particles carry with them from their shared preparation. John Bell proved in 1964 that any theory based on local hidden variables would make different predictions than quantum mechanics, and experiment after experiment has sided with quantum mechanics. The entanglement is genuine. The instantaneous connection across arbitrary distance is genuine. You can immediately see why this matters to anyone thinking about faster-than-light communication. If measuring one particle instantly affects the state of another particle anywhere in the universe, then entanglement seems to provide exactly the mechanism needed to send information faster than light. Measure the particle here. Observe the correlated result there, and you have apparently transmitted something across a cosmic distance without waiting for any signal to travel. The problem is that the correlation cannot be used to transmit information. This is the content of the no-signaling theorem, one of the most important and repeatedly confirmed results in quantum information theory. When you measure an entangled particle, you get a result. The result is random. Quantum mechanics does not determine in advance which of the possible outcomes will occur. You measure and you get spin up or spin down, some probability for each, and the specific outcome is unpredictable, even in principle. The distant partner particle shows a correlated result, but that result is equally random from its own perspective. The observer at the distant particle sees a sequence of random outcomes that is consistent with the correlations quantum mechanics predicts, but indistinguishable from a sequence of random outcomes with no entanglement at all, until they communicate with the first observer through a conventional channel and compare notes. The information about which outcome actually occurred at the first particle travels at the speed of light or slower through that conventional channel. The entanglement correlation itself carries no information because neither observer can control which outcome they get. Sending a message would require choosing your particle's outcome, and the laws of quantum measurement forbid this. The randomness is not a technological limitation. It is a fundamental feature of quantum mechanics. Every serious proposal to use quantum entanglement for faster-than-light communication has failed at exactly this point. The physics is consistent, and the prohibition is genuine. Entanglement remains one of the deepest mysteries in all of science. A confirmed non-local connection that somehow carries no information and conveys no message. The dream of quantum shortcuts was real. The shortcuts themselves were not available. In 1967, a physicist named Gerald Feinberg at Columbia University published a paper in Physical Review that asked a question most of his colleagues would have dismissed as a theoretical curiosity. What if, instead of trying to accelerate something past the speed of light, you posited the existence of particles that had always been faster than light and asked what their properties would have to be? The logic of special relativity contains a boundary, not merely a speed limit, but a mathematical wall. At the speed of light, the energy required for acceleration diverges to infinity. Nothing that starts below the speed of light can reach it because the energy demand becomes infinite before it arrives. This is the familiar argument for why nothing material can achieve light speed. But Feinberg pointed out that the argument applies only to particles transitioning through the speed of light from below. The mathematics does not forbid the existence of particles that have always existed above the speed limit and have never transitioned through it at all. Such particles would occupy a separate sector of relativity's kinematic landscape. Feinberg worked out the properties these hypothetical particles would need to possess. The results were deeply strange. For an ordinary particle, the energy-momentum relation of special relativity requires that the square of the particle's mass be positive. The mass is a real number, and the particle's rest energy is real and positive. For a particle permanently above the speed of light, the mathematics demands that the square of the mass be negative, meaning the mass itself must be imaginary in the mathematical sense, a multiple of the square root of -1. Feinberg named these hypothetical particles tachyons, from the Greek word for swift. They would always travel faster than light. They could never slow to light speed, just as ordinary particles can never accelerate to it. The speed of light would function as a lower bound for tachyon velocities rather than an upper bound. Slow a tachyon down and its energy increases. Give it less energy and it moves faster. The tachyon's kinetic universe runs exactly backward from everything familiar. The theoretical problems appeared immediately, and they were severe. If tachyons exist and can carry information, then faster than light information transmission becomes possible. Special relativity, combined with the principle that the laws of physics are the same in all inertial reference frames, implies that faster than light information transmission allows information to travel backward in time in some reference frames. A message sent via tachyon could, from the perspective of a suitably moving observer, arrive before it was sent. This is the tachyonic antitelephone, a causal paradox that most physicists regard as evidence that tachyons carrying information cannot exist in a consistent universe. More fundamentally, no experiment has ever detected a tachyon. Particle accelerators have probed the structure of matter down to scales far smaller than atomic nuclei without finding any evidence of particles with imaginary mass. Every known fundamental particle carries positive mass squared. Every decay product, every collision result, every quantum field measurement has been consistent with a universe in which tachyons simply do not appear. They are permitted by a certain reading of special relativity's mathematics and absent from every physical measurement ever taken. The tachyon represents the outer edge of the catalogue. Every approach had been surveyed. The modified spacetimes, the engineered geometries, the quantum correlations, the hypothetical particles. Each one ran into a wall constructed from the same materials: exotic matter, causal paradox, or experimental absence. But something had changed regardless. A NASA physicist had taken the Alcubierre metric seriously enough to build an experiment around it. The agency that put human beings on the moon had a researcher inside its walls doing the math on warp bubbles. In 2001, a British engineer named Roger Scheuer filed a patent that seemed to rewrite the rules of propulsion. The device was called the EmDrive, and its design was so simple it felt like a dare. Take a sealed copper cavity shaped like a truncated cone, pump microwaves into it. According to Scheuer, the cavity would produce thrust. No propellant escaped the chamber. No exhaust exited the system. The microwaves bounced around inside, and the whole assembly allegedly pushed itself forward. You can see the problem immediately. Newton's third law demands that every action produce an equal and opposite reaction. A rocket works because it throws mass out the back. An ion thruster works because it accelerates charged particles through a nozzle. The EmDrive threw nothing. It claimed to generate force from a closed system, which violates conservation of momentum, one of the most thoroughly tested principles in all of physics. Scheuer argued that radiation pressure differences between the wide and narrow ends of the cone created a net force. Physicists pointed out that such differences cancel inside a closed container. The math had been settled for centuries, and yet the device refused to disappear. A Chinese research group reported measuring thrust in 2012. EagleWorks, a small advanced concepts lab at NASA's Johnson Space Center, published results in 2016, claiming they had also detected force from a similar cavity. The paper passed peer review, and headlines erupted: propellantless propulsion, reactionless drives, the stars within reach. We need to understand what happened inside those labs. The forces being measured were extraordinarily tiny, on the order of millionths of a Newton. At that scale, thermal expansion, electromagnetic interference, outgassing from heated surfaces, and interaction with Earth's magnetic field all produce artifacts that mimic thrust. Every one of these confounds was raised by outside physicists, and every one was difficult to fully eliminate in the existing experimental setups. The EagleWorks team acknowledged significant uncertainties, but maintained their signal was real. The decisive test came from Dresden. In 2021, a team at the Technische Universität Dresden, led by Martin Tajmar, one of the most meticulous experimentalists in the field, built a series of EmDrive variants and tested them inside a sophisticated vacuum chamber with improved shielding and mounting. They found that when they accounted for thermal effects, specifically the expansion of cables and supports as the microwave generator heated the cavity, the anomalous thrust vanished entirely. Every measurement that had previously suggested propellantless force could be explained by the apparatus warming up and shifting on its mount. The signal was real, but it came from the test rig, not from new physics. The EmDrive was dead. The copper cavity produced no thrust, violated no laws, and opened no doors to the outer solar system. Scheuer continued to insist his design worked, and a small community of enthusiasts kept building homemade versions in garages and posting results online. But the scientific case was closed. The The Dresden results were clean, reproducible, and consistent with known physics. Here is the part that stings. For nearly 20 years, the EmDrive consumed attention, funding, laboratory time, and public hope. Talented researchers spent years chasing a signal that turned out to be heat. The device never had a plausible theoretical mechanism, and the experimental evidence was always marginal. Yet it persisted because we wanted it to. And that desire, the sheer gravitational pull of wanting faster propulsion, tells us something important about ourselves that we rarely examine honestly. The EmDrive story reveals a pattern that extends far beyond one copper cavity. When we look at the history of faster-than-light research, a recurring theme emerges. The strength of our desire for a result bends how carefully we evaluate the evidence supporting it. This tendency has a name in psychology. Motivated reasoning describes the process by which our emotional investment in a conclusion shapes our evaluation of the data. We do not falsify our beliefs cleanly. We set a higher bar for evidence that contradicts what we want and a lower bar for evidence that confirms it. In the context of interstellar travel, the emotional stakes are enormous and the distortion runs deep. Consider how the EmDrive results propagated through the scientific community. When the EagleWorks paper appeared, the peer review was real, but the journal was modest. The measured forces were tiny and the error bars were wide. Any other claim with that level of statistical significance would have been treated as preliminary and tentative. Instead, it generated global headlines. Journalists wrote about warp drives and Mars in 70 days. Social media amplified the most optimistic interpretations. The normal machinery of scientific caution, the insistence on replication, the careful scrutiny of systematics, slowed to a crawl because the result was so seductive. We have seen this pattern before. In 1989, Stanley Pons and Martin Fleischmann announced cold fusion at a press conference. The result, if true, would have solved the energy crisis overnight. Laboratories worldwide rushed to replicate. Most failed, and within a year, the scientific consensus had turned against the claim. But a dedicated community of believers persisted for decades, convinced that the mainstream had overlooked something genuine. The parallel to the EmDrive community is striking. Both groups were sustained by the magnitude of what the result would mean if true. The hunger for propellantless propulsion also shaped how we processed the theoretical objections. Physicists who pointed out that the EmDrive violated conservation of momentum were sometimes dismissed as closed-minded gatekeepers, unwilling to consider revolutionary ideas. The framing shifted from, "Does this violate established physics?" to "Maybe established physics is incomplete." That second framing is always technically possible, which made it hard to counter in public discourse. Relativity was revolutionary once. After all, maybe the EmDrive was the next revolution. But revolutions in physics come with extraordinary evidence. Einstein did not simply assert that time was relative. He provided a mathematical framework that made precise, testable predictions that were subsequently confirmed with increasing accuracy over the following century. The EmDrive offered no such framework. It offered a copper cone and a marginal signal. The asymmetry between the size of the claim and the strength of the evidence should have been disqualifying from the start. For many physicists, it was, but for the broader public, and for a portion of the aerospace community, the dream was too powerful to abandon on merely technical grounds. We carry this lesson forward as we evaluate every other concept in the faster-than-light catalogue. The Alcubierre drive is real mathematics, but the exotic matter it requires has never been observed in macroscopic quantities. Quantum tunneling permits particles to cross barriers, but no information has been transmitted faster than light using entanglement. Each of these ideas deserves honest evaluation, and honest evaluation demands that we interrogate our own excitement with the same rigor we apply to the physics. In 2021, a physicist named Lentz published a paper from the University of Göttingen that genuinely shifted the landscape of warp drive research. The title was dense, as theoretical physics papers tend to be, but the core result was elegant and startling. Lentz had constructed a class of warp drive solutions to Einstein's field equations that required only positive energy densities. Every previous warp metric, from Alcubierre onward, had demanded exotic matter with negative energy to function. Lentz found a way around that requirement. To understand why this matters, recall the central obstacle that had stalled warp research for nearly 3 decades. The Alcubierre metric worked beautifully as geometry. Space-time contracted ahead of the ship and expanded behind it, carrying the vessel forward at arbitrary speed while the interior remained flat and calm. The catch was always the energy conditions. General relativity allows many geometric solutions, but the universe imposes constraints on what kinds of matter and energy can actually produce those geometries. The weak energy condition states that any observer should measure non-negative energy density. The Alcubierre drive violated this condition everywhere along the bubble wall. Building it would require matter that, as far as anyone could demonstrate, did not exist outside quantum fluctuations at microscopic scales. Lentz approached the problem differently. Instead of starting with a desired geometry and working backward to find the required energy, he started with the energy conditions and searched for geometries that satisfied them. The resulting solutions took the form of solitons, stable, self-reinforcing wave packets in the fabric of spacetime that propagate without dispersing. These solitons could travel at superluminal speeds while being sourced entirely by positive energy matter. The reaction from the physics community was cautious but genuine. Lentz had not made an error that anyone could identify. The mathematics was internally consistent. The solutions existed within general relativity without requiring modifications to the theory. For the first time in the history of warp research, someone had demonstrated that faster-than-light travel might be compatible with the energy conditions that our universe actually obeys. We should be precise about what Lentz accomplished. He did not design a spacecraft. He did not propose a construction method. He did not solve the engineering challenges or address the causal paradoxes that superluminal travel introduces. What he did was remove the single most devastating theoretical objection to warp drives. For 27 years, every serious physicist who examined the Alcubierre metric could point to exotic matter and say, "This requires something that probably cannot exist in bulk." After Lentz, that specific objection no longer applied to all warp solutions. Some valid configurations needed only the kind of energy that ordinary matter provides. The paper attracted attention from researchers who had previously dismissed warp drives as mathematical curiosities with no physical relevance. If positive energy solitons were valid solutions, then the theoretical barrier between warp research and mainstream physics had become thinner. The question shifted from whether any physically reasonable warp metric could exist to whether the remaining engineering obstacles could ever be addressed. That shift was subtle but profound, and it opened a door that many had assumed was permanently sealed. The Lentz solitons were real mathematics. The solutions sat comfortably within general relativity, obeyed the energy conditions, and propagated at superluminal velocities. For anyone who had followed the decades of warp research and watched every proposal collide with the exotic matter barrier, this felt like a genuine turning point. But turning points in theoretical physics come with fine print, and the fine print on the Lentz result was extensive. Start with the energy requirements. The solitons required no exotic matter, which was the breakthrough. They did, however, require staggering quantities of ordinary energy. When physicists calculated the total energy needed to generate even a modest soliton, the numbers exceeded anything our civilization could produce. We are talking about energy scales comparable to the mass energy of entire planets. The conversion factor between mass and energy, established by relativity, means that producing the necessary energy would require converting enormous quantities of matter with perfect efficiency. Our best energy sources, nuclear fission and fusion, convert less than 1% of their fuel mass into usable energy. The gap between what the solitons required and what human technology could deliver spanned many orders of magnitude. Then there was the question of how to shape the energy distribution. The Lentz solutions demanded a very specific configuration of energy density throughout the soliton structure. Generating the right total amount of energy was one challenge. Arranging it with the required precision was another entirely. No known physical process could sculpt an energy distribution into the exact form the solitons demanded. We would need to control space-time curvature directly, and we had no mechanism, even in principle, for doing so at the scales required. The causal structure of the solitons also remained unresolved. Any superluminal solution to Einstein's equations raises questions about closed time-like curves, paths through space-time that loop back on themselves and permit travel into the past. The Alcubierre drive faced this challenge, and the Lentz solitons inherited it. Lentz did not address the causality problem in his original paper, and subsequent analysis suggested that the solitons might indeed permit configurations where causal paradoxes arose. Resolving this would require either a proof that the problematic configurations were physically unrealizable or a deeper theory that modified general relativity at the relevant scales. We should also note what the result did to expectations within the research community. Some commentators seized on the Lentz paper as proof that warp drives were around the corner, that the engineering challenges would fall like dominoes once the theoretical foundation was secure. This interpretation leaped over the enormous distance between a valid mathematical solution and a buildable device. History offers many examples of theoretically permitted phenomena that remain permanently beyond practical realization. The laws of physics permit a bridge of solid diamond spanning the Atlantic Ocean. No law forbids it. Yet no one draws up construction plans. The Lentz result was valuable precisely because it was limited. It answered one question, and one question only. Can warp drive geometries exist without exotic matter? The answer was yes. Every subsequent question, about energy scales, control mechanisms, causal consistency, and construction feasibility, remained open. Recognizing this distinction matters, because it determines whether we treat the result as a foundation for further research or as a premature declaration of victory. The history of warp drive science is littered with the wreckage of overinterpretation. The Lentz solitons deserved better than to become the next casualty. By the early 2020s, warp drive research had accumulated nearly 3 decades of proposals, modifications, critiques, and counter-proposals. The Alcubierre metric had spawned variants. The energy estimates had been revised downward, then challenged, then revised again. Exotic matter alternatives had appeared. Positive energy solutions had emerged. The field was productive, but it was also scattered. Different researchers used different conventions, different energy conditions, and different definitions of what qualified as a warp drive. Comparing results across papers required translating between frameworks, and legitimate advances sometimes went unnoticed because they were written in a dialect that only their authors' immediate circles could parse. In 2021, Alexei Bobrik and Gianni Martir, working through Applied Physics, a private research organization, published a paper that attempted to impose order on this sprawl. Their contribution was taxonomic rather than generative. Instead of proposing a new warp metric, they built a classification system for all warp metrics. The paper established a general framework within which the Alcubierre drive, the Lentz solitons, the Van den Broek modification, and every other warp proposal could be described using a common mathematical language. The framework rested on a simple but powerful observation. Every warp drive proposal, regardless of its specific geometry, shared a common structure, a region of modified spacetime that carried a payload through the universe at some effective velocity. The differences between proposals lay in the specifics of how that region was constructed, what energy conditions it satisfied, and what velocities it could achieve. Bobrik and Martir formalized these distinctions and created a parameter space within which any proposed warp geometry could be located and compared. This might sound like bookkeeping rather than breakthrough, and in a narrow sense it was. The taxonomy did not solve the energy problem, the exotic matter problem, or the causality problem. It did not bring a working warp drive one step closer to construction, but it performed a function that every maturing scientific field eventually requires. It made the territory legible. Before the Bobrick and Martier paper, a researcher entering the warp field had to navigate a thicket of independent proposals, each with its own notation and assumptions. After the paper, the same researcher could see the entire landscape laid out on a single map. The classification also revealed structural relationships that had been obscured by the fragmented literature. Some warp metrics that appeared different on the surface turned out to be members of the same family when expressed in the common framework. Others that had been assumed equivalent revealed hidden distinctions. The taxonomy exposed gaps, regions of the parameter space where no one had yet proposed a solution but where solutions might exist. Applied physics positioned itself as a serious organization pursuing warp research with institutional resources, peer-reviewed publications, and a stated long-term goal of making interstellar travel physically realizable. The Bobrick and Martier paper was its foundational document, the equivalent of a geological survey before mining begins. Whether anything would eventually be extracted from the territory remained uncertain, but the map itself was a contribution. Science advances through both discovery and organization, and at the stage where warp drive research stood in the early 2020s, organization was arguably the more urgent need. The field finally had a common language, and that language would shape every conversation that followed. While theorists were debating exotic matter and publishing warp metrics in academic journals, one government had already placed a quiet bet on the possibility that breakthrough propulsion might be real. In 1996, NASA established the Breakthrough Propulsion Physics Program under the direction of Mark Millis, a propulsion engineer at the Glenn Research Center in Cleveland, Ohio. The program's mandate was straightforward and audacious: evaluate whether any known or speculative physics could enable interstellar travel within a human lifetime. Millis had been thinking about the problem for years before the program launched. His approach was methodical rather than visionary. He did not assume that faster-than-light travel was possible. Instead, he identified the specific physics questions that would need to be answered for any form of breakthrough propulsion to work, and he funded small-scale research projects aimed at those questions. The program operated on a modest budget, roughly $1 million per year, which was trivial by NASA standards, but sufficient to support a handful of university grants and in-house experiments. The research portfolio reflected the program's agnostic stance. Some projects investigated whether inertia could be modified, a possibility suggested by certain interpretations of quantum vacuum interactions. Others examined whether gravitational effects could be generated by electromagnetic means. A few explored the theoretical foundations of the Alcubierre metric, which had been published just 2 years before the program began. The common thread was intellectual honesty. Each project was evaluated against clear success criteria, and negative results were treated as genuine contributions rather than failures. By 2002, the Breakthrough Propulsion Physics program had completed its planned research cycle. The results were sobering. No experiment had produced evidence of modified inertia. No electromagnetic gravity generation had been observed. The Alcubierre metric remained theoretically fascinating but practically inaccessible. Millis compiled the results into a comprehensive report that documented what had been tried, what had been learned, and what remained unknown. The program was defunded as part of broader budget restructuring at NASA, and the agency's attention shifted toward nearer-term goals. But Millis did not abandon the mission. In 2004, he founded the Tau Zero Foundation, a non-profit organization dedicated to continuing the research agenda that NASA had started. The foundation operated outside the constraints of government funding cycles and political priorities. It supported theoretical work, hosted conferences, and maintained a network of researchers who continued to explore breakthrough propulsion concepts. The name came from a Poul Anderson novel about a starship that accelerates without limit, a fitting emblem for an organization defined by persistence in the face of discouraging results. The Breakthrough Propulsion Physics program and its successor established an important precedent. They demonstrated that serious, methodical evaluation of far future propulsion concepts could be conducted within institutional frameworks. The work was transparent, peer-reviewed, and honest about its limitations. It produced no breakthroughs, but it produced something almost as valuable, a rigorous catalogue of what did not work and why. Every subsequent researcher in the field could build on that foundation rather than repeating the same dead ends. And the quiet admission embedded in the program's existence that even NASA thought the question was worth asking gave the field a legitimacy it had previously lacked. We have surveyed the catalogue. Now we lay every concept on the table and run the numbers with brutal honesty, because the distance between theoretical possibility and engineering reality determines whether these ideas belong in mission plans or remain permanently shelved in the realm of thought experiments. Start with the Alcubierre drive-in, its original formulation. The energy requirement to generate a warp bubble large enough to carry a small spacecraft was initially estimated at roughly the mass energy equivalent of Jupiter. Later refinements by Van den Broek, by adjusting the bubble geometry, and by Chris Van den Broek and others who thickened the bubble wall and shrank the throat, reduced that figure substantially. The most optimistic recent estimates place the energy requirement at something comparable to the mass energy of a few hundred kilograms, assuming perfectly efficient conversion and an idealized bubble shape. That sounds approachable until you remember that converting even 1 kilogram of matter entirely into energy releases a yield equivalent to the largest thermonuclear weapons ever detonated. Converting hundreds of kilograms with perfect efficiency and directing the output into a specific spacetime geometry exceeds any technology we can currently envision. Then there is the exotic matter problem. The original Alcubierre solution requires negative energy density throughout the bubble wall. The Casimir effect demonstrates that negative energy densities exist at microscopic scales between conducting plates separated by nanometers. Scaling this to macroscopic dimensions would require plates of astronomical size or an entirely different mechanism for generating negative energy that no one has proposed. The Lentz solitons avoid exotic matter but substitute an energy requirement so large that the practical difference vanishes. Consider propellantless approaches next. The EmDrive has been definitively debunked. No other reactionless drive has survived rigorous testing. Conventional propulsion, even at its theoretical best, remains constrained by the rocket equation, which demands exponentially increasing fuel mass as the desired velocity approaches the speed of light. A spacecraft accelerating to 90% of light speed using fusion propulsion would require a fuel-to-payload ratio so extreme that the vehicle would consist almost entirely of fuel tanks. Quantum approaches fare no better in practical terms. Quantum tunneling operates at subatomic scales and does not permit macroscopic objects to traverse barriers. Quantum entanglement transmits no usable information faster than light. The quantum vacuum fluctuations that some have proposed as energy sources produce effects so small that extracting useful work from them remains speculative at best. The honest summary is stark. We possess theoretical frameworks that permit faster-than-light geometries within general relativity. We possess experimental confirmation that negative energy exists at the quantum scale. We possess no mechanism for bridging the gap between these facts and a functioning propulsion system. The gap spans energy scales, material requirements, and fundamental questions about causality. Every item in the catalogue, when subjected to engineering scrutiny, reveals the same conclusion. The physics may permit it in principle, but the universe has placed the required resources far beyond our current reach. So what exactly would need to change? If we strip away the speculation and the optimism and ask plainly what breakthroughs would be required before any faster-than-light technology became physically realizable, 3 distinct challenges emerge. Each one is formidable on its own. Together, they define a research program that might span centuries. The first breakthrough is stable, macroscopic negative energy. The Casimir effect proves that quantum field theory permits regions of space where energy density drops below the vacuum baseline. But these regions are microscopic, existing between plates separated by distances comparable to the wavelength of visible light, and the total energy involved is vanishingly small. A functional warp drive, at least in the Alcubierre family of solutions, requires negative energy distributed across a shell meters wide, sustained for the duration of the journey. Moving from Casimir scale effects to warp bubble scale structures represents a leap comparable to moving from static electricity to a continental power grid. We would need either a method for amplifying quantum vacuum effects by many orders of magnitude, or the discovery of an entirely new physical phenomenon that produces negative energy at macroscopic scales. Neither path has a clear starting point in current physics. The second breakthrough is direct manipulation of spacetime geometry. General relativity describes how matter and energy curve spacetime, but the relationship is one-directional in practice. We observe curvature produced by existing mass distributions. We do not possess the ability to engineer specific curvature profiles independent of those distributions. A warp drive requires sculpting spacetime into a precise configuration, a contraction here, an expansion there, with tolerances that allow the interior to remain flat while the exterior deforms superluminally. Achieving this would require something analogous to a spacetime actuator, a device that converts input energy into targeted geometric deformation. No theoretical framework currently describes how such a device would function, and no experiment has demonstrated deliberate curvature manipulation at any scale. The third breakthrough is a resolution to the causality problem. Any superluminal travel framework within general relativity permits, under certain conditions, the construction of closed time-like curves, effectively allowing communication with or travel into the past. The logical paradoxes this introduces are profound and may indicate that superluminal solutions, while mathematically valid, are physically forbidden by some deeper principle not yet incorporated into our theories. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel, but no one has proven this conjecture from first principles. A civilization attempting to build a warp drive would need either a proof that their specific implementation avoids all closed time-like curves, or a complete theory of quantum gravity that resolves the paradox at a fundamental level. We possess neither. Each of these three requirements intersects with the others. Negative energy at macroscopic scales might enable space-time manipulation, which might resolve or exacerbate the causality problem, depending on the specific implementation. Progress on any one front would reshape the landscape for the other two. The research program is deeply interconnected, which means that a breakthrough in one area could cascade into rapid progress across all three, or that an impossibility result in one area could foreclose the entire enterprise. Let us conduct a thought experiment. Set aside the question of whether faster-than-light travel is possible, and ask instead what kind of civilization would build such a thing. The answer illuminates where we stand and how far we would need to travel, not in miles but in capability. In 1964, the Soviet astronomer Nikolai Kardashev proposed a scale for classifying civilizations by their energy consumption. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10 to the 16th watts. A Type 2 civilization captures the entire energy output of its star, approximately 10 to the 26 watts. A Type 3 civilization commands the energy resources of an entire galaxy. The scale is crude, but it provides a useful yardstick for measuring the gap between aspiration and capacity. Humanity, in the 2020s, consumes roughly 10 to the 13th watts. We fall short of Type 1 status by several orders of magnitude. We derive most of our energy from burning fossil fuels, a process so primitive that a Kardashev Type 1 civilization would regard it the way we regard burning dung. Our nuclear capabilities, both fission and the still unrealized promise of controlled fusion, could in principle push us toward the lower boundary of Type 1, but we have not achieved this transition and may not for another century or more. A warp drive, even in its most optimistic formulations, requires energy on the order of stellar-scale processes. Converting the mass energy of even modest quantities of matter demands efficiencies that our current technology cannot approach. The civilization that builds a warp drive would need to be, at minimum, a robust Type 1 civilization, transitioning toward Type 2, one that has mastered controlled fusion, developed space-based energy infrastructure across its solar system, and achieved manufacturing capabilities sufficient to engineer structures at planetary scales. Such a civilization would look nothing like ours. Its economy would be post-scarcity in the material sense. Its scientific institutions would have centuries of continuous research behind them, building on theoretical foundations we have not yet laid. Its engineering traditions would include the routine manipulation of forces and materials that we currently observe only in astrophysical contexts. The gap between 21st century humanity and a warp-capable civilization is comparable to the gap between a medieval blacksmith and a modern semiconductor fabrication plant. The blacksmith and the engineer share fundamental physical laws, but the distance in applied knowledge, institutional capacity, and accumulated infrastructure is vast. This perspective can feel deflating, but it also clarifies the mission. We are not trying to build a warp drive in the 2020s. We are trying to lay the theoretical and experimental foundations that a future civilization might use. The Alcubierre metric, the Lentz solitons, the Bobrick and Martyr taxonomy, the breakthrough propulsion physics reports. These are not failed engineering projects. They are early cartography, maps drawn centuries before the ships that will sail those waters have been designed. Our role is to make the maps as accurate as possible and to pass them forward honestly, without inflating our progress or deflating our purpose. Return now to Proxima Centauri, the nearest star beyond our own, sitting 4.25 light-years away. We opened this journey with that destination, and everything since has been an attempt to answer a single question: how do we get there? We have surveyed the entire catalogue of proposals. Now we reframe the mission with everything we have learned and confront the gap between ambition and reality with unflinching clarity. Without warp technology, the Proxima mission relies on conventional physics pushed to its theoretical limits. The most promising near-term concept remains the light sail, propelled by a ground-based or space-based laser array. The Breakthrough Starshot initiative envisions a gram-scale probe accelerated to 20% of the speed of light, arriving at Proxima in roughly 21 years. The probe would be tiny, carrying miniaturized instruments capable of basic imaging and spectroscopy. It would flash through the Proxima system at blistering speed, with only minutes to collect data during its closest approach. There would be no deceleration, no orbit, no landing. The probe would continue into interstellar space, its mission complete in the brief window of its flyby. A crewed mission without warp technology would look entirely different. Chemical rockets are out of the question. Nuclear pulse propulsion, the concept behind Project Orion, could theoretically achieve a few percent of light speed, placing Proxima roughly a century away. Fusion propulsion, if we ever master it, might push that to 5 or 10% of light speed, reducing the journey to 40 or 50 years. The crew would need to survive in a sealed environment for the duration, requiring advances in life support, radiation shielding, and closed-loop ecology that we have not yet demonstrated even for a Mars transit. The spacecraft itself would be enormous, a generation ship in all but name. Now, reimagine the same mission with a functioning warp drive. The specifications are generous. Assume a bubble capable of effective superluminal transit, powered by an energy source that a Type 1+ civilization could provide. The spacecraft departs from Earth orbit inside its warp bubble. The journey to Proxima, 4.25 light-years, takes days or weeks, depending on the effective velocity of the soliton. The crew experiences normal time, normal gravity, and normal physics inside the bubble. They arrive at Proxima with their velocity matched to the local frame, orbit the star, deploy instruments, study the planet Proxima b in detail, and return home within a human career span. The contrast between these two scenarios captures everything this documentary has been about. One version of the Proxima mission is achievable within decades, but it yields a fleeting snapshot from a disposable probe. The other version is a full scientific expedition, but it requires breakthroughs so profound that they may lie centuries in our future. We are caught between what we can do and what we want to do, between the physics we have mastered and the physics that masters us. The Proxima mission, in either form, represents the honest state of our ambitions. We know exactly where we want to go. We are still learning what it will cost to get there. Step back now from the equations, the energy estimates, the bubble geometries, and soliton parameters. Step back from the laboratory measurements and the debunked prototypes and the classification frameworks. We have spent this entire journey inside the mathematics, and the mathematics has been honest with us. It has shown us doors, and then shown us the walls behind those doors. It has offered geometries that our universe might permit, and then demanded resources our civilization cannot provide. Every chapter has been a negotiation between human ambition and physical law, and the law has won every round. But something else has been happening alongside that negotiation. Every physicist who worked on these problems, from Miguel Alcubierre sketching his metric on a notepad to Eric Lentz searching for positive energy solitons in Göttingen, was driven by the same impulse. They looked at the distance between stars and refused to accept it as permanent. The refusal was not irrational, it was rooted in the deepest tradition of science itself, the conviction that understanding changes what is possible. We did not always know how to leave the surface of the Earth. We did not always know how to split the atom. The distance between ignorance and capability has been closed before, and the memory of those closings sustains the effort to close it again. The catalogue we have assembled is incomplete by design. New proposals will appear. Someone will find a way to reduce the energy requirements by another order of magnitude. Someone else will discover a property of quantum gravity that reshapes the causality debate. The field is young, barely 3 decades old if we date it from the Alcubierre metric, and young fields are full of surprises. The history of physics teaches us that the most transformative breakthroughs often come from directions no one anticipated. Maxwell did not set out to unify electricity and magnetism with light. Einstein did not set out to make nuclear energy possible. The path from fundamental insight to practical consequence is rarely straight and never predictable. What we carry forward from this survey is a specific kind of hope, one calibrated by honesty. We know what we need. We know what we lack. We know the difference between a mathematical possibility and an engineering blueprint. We know that motivated reasoning can corrupt even rigorous research programs, and we have learned to guard against it. We know that the civilization capable of building a warp drive is separated from ours by centuries of development, and we know that every contribution to the theoretical foundations matters because those foundations will outlast us. The light from Proxima Centauri takes 4 years and 3 months to reach your eyes. When you look at that star tonight, you are seeing it as it was before you started watching this documentary. The distance is real, the time is real, and the effort to close that distance, to find some way across the gap that light itself requires years to traverse, is one of the defining projects of our species. We may not be the generation that builds the ship. We are the generation that studies the ocean. The tachyon represents the outer edge of the catalogue. Every approach had been surveyed. The modified spacetimes, the engineered geometries, the quantum correlations, the hypothetical particles. Each one ran into a wall constructed from the same materials: exotic matter, causal paradox, or experimental absence.